Hi there, I'm Hao, and this is just another video of me solving random net code problem. Given the root of a binary tree where every node has a unique value and a target integer k, return the value of the nearest leaf node to the target k in the tree. Okay, and the nearest leaf node mean the nearest to the leaf mean the least number of edges travel, right, on a binary tree to the originating leaf node. So because we are counting the number of edges here, which means we can go up to the parents as well, right? But this is not a regular breadth search solution. So if we only have three nodes here, right, the target is one, then the nearest leaf node, it can be either two or three, right? The leaf node means the node has no children because it is one is one step away from two and three or three. In the second example, right, the answer would just be one because the target is one, would just be the root itself because the root itself is already a leaf node. Right, if we look at the last example here, k is 2, right? And the distance to the leaf node 6 is 1, 2, 3, 3 step, right? But the distance to this leaf node 3. So we have like two leaf nodes, right, in our tree here. And the distance from 2 to leaf node 3 is only 2 steps, right? So the answer is 3. Because as mentioned earlier, we are counting the number of edge, 1, 2, right? And this one they have 1, 2, 3, which means we can go back up to the parent. Okay. Um. Okay, we know that all the value in the tree are unique. There exists some node in the tree where node of val equal to k, so the target k will always be valid, right? That makes sense. We don't have to worry about the edge case. And then as we see, we need to go back up to the parent, right? But we don't have the parent attribute in the tree node definition. So we can build one, right? So if we think about it, if we always, uh, okay, assuming we have the parent pointer to from any node to its parents, right? Assuming we already have like the parent here, right? Equal to something, right? If we found a target, which is 2 here, we can run the depth first search on this target to find the distance from every node to the leaf node, from the target to the leaf node, right? So we can keep track of an, let's say a hash map here or an array. Yeah, hash map. Right. And every time we run the depth first search, we would just like increase the distance by one, right? Just like 1, right? 2, 3, right? This side don't have anything, so just be 0, right? So that doesn't count. This is not the leaf node. But we have also have to we check the left, right? We need to run a depth first search on the left, on the right, right, and on the parents of the target, right? So left, right, and parent, right? And so if we go to the parents, right, then we need to also check the left, right, and parents, right? The parent of this node is null, right? So that doesn't count. You can check the right, right here, which is only one edge, right? So whenever we reach a leaf node, we will store the distance to this leaf node, right? We will store the distance to this leaf node and also the node itself, right? Because we want to because the Braum asks for the value of the leaf node, right? So we need to keep track of the distance and the leaf node itself, right? Another thing that we need to think about is that because we are going back up to the top, right? Which means if we go here back to one, right? And one can go back to two, and two can go back to one again, which keeps us in an infinite loop, right? Normally, a tree, we cannot go back to the parent. In that case, right, we don't we will guarantee that we will reach the end of the tree eventually. But because we are able to go back up to the top, we need to keep track of the visited node, right? So we can have a visited set, right, to keep track of the visited node, right? So in that case, we won't run into an infinite loop. So that is the general idea, right? So the first step is to set up, set the parent pointer, set the parent pointer for all node, right? And then we need to find the target node. So how do we set the parent pointers? So we can just iterate through each and every single node, right? And just set the parent. When we add the left and the right children into our queue, we can just set the parent, right, of that node to be the current node, right? So we can iterate through every single node and set up the parent, right? And along the way, when we're doing that, we can also find the target node. Okay, after that, what do we want to do? We want to find the distance, right? Of so distance of target node to all leaf node, right? Right. Using DFS, right? And we need to also keep track of the visited node because we need to go upward, right? And after we have the distance from the target node to every single leaf node, we can sort it, right? And find the smallest distance, and we can return the leaf node with the shortest distance. But sorting is n log n, right? So we can just use a for loop, iterating through the whole array, keeping track of the minimum node and the minimum distance, right? We can return the minimum node value at the end. And we are guaranteed that the target will always exist. This operation, we iterating through every single node, so that is O of n. The step two is also O of n, right? Because we have to keep track of the visit node, so we will never visit a node twice. So, and for the third step, right, we find the mean distance, right, and return the mean diff node value, right? This is also O of n. So our total runtime will be O of n. For the stay, because we need to keep track of our visited node, this is also O of n. Okay, so that is the runtime and the general idea here. So let's quickly walk through an example here, right? So let's say I will demonstrate step two here because I think this is the most crucial step. So let's say we start at two. We start at two. We keep track of the node right here. Let's put it here. So we put two here, right? Start from two, and we go to the parent, the left and the right, right? So let's go to the parent first. So this is one, right? It is our distance, right? From one, we add one to our visit set, right? We check the left, we check the parent, right? Which is no. If it is no, it is our base case, right? We just return and don't do anything. And then we check the left, right? The left, because two is already in the set, so we skip the left range, and we will go to the right range, right? To the right range, which is three here. we add the two the set and we increase the distance, right, by 1, which is 2 here, right? So now because we have a couple of base cases, right? If we reach null, we just return, or if we reach a leaf node, right? And we want to keep track of the, the node, right? Which is 3 and the distance to that node, right? The node and then the distance, right? The distance from the target node to the leaf node, right? So the second base case is when we see a leaf node. So after that, we finish looking at the parents, right? This part. So we continue to the left here because the right don't have anything, right? We just go to the left, 4 here. So we add 4, we increase the distance, right? 4, we look at the parent, 2 is already in here. So we don't do anything. Look at the left, 5, we add 5, right? Increase the distance. We look at the parent, 4. 4 is already in the set, so we don't do anything. Go to the left, and increase the distance, add 6 here, right? 6, look at the parent, which is 5. 5 is already in the set. We finish, right? Look at the right side, and we don't have, we just have no, right? So when we reach 6 here, which is a leaf node, right? We want to keep track of the node, leaf node value 6 and the distance, right? Just 4 here. Right? And after that, we have an array, a 2D array storing the distance and the node leaf node value. So you can just iterate through this and find the minimum distance and return the leaf node value. All right, so let's code this up. So the first step is to we have to set the parent pointer, right? Set the parent pointers and target node starting from the root, starting from the root. Okay. The if root is low, right? Can just return. Let's just call this node so we don't confuse ourselves with the variable in the outer function. Right? We can do node of parent equal to parent. Right? Let's also keep track of the parent node and the parents, and the parent of the group will just be null, right? And then we can just keep going on the left and on the right. Node the left. So who is the parent of the node the left? If we are at 1, right? Node the left is 2. So the parent of 2 will be 1. Right? Similarly, for the right side. Okay, so we finished the first part, right? Set the parent pointers. That is for the first part. The second part is we can set the target node, right? So we can do let's see, we can do if node.val equal to k, right? And we can set the target node equal to the node itself. And of course, we need to create the target node here equal to null. Right. Okay. So that is the first step. What is the second step? The second step is to now we have the pattern relationship, right? So we can iterating through the tree again, but starting from the target node, and we can run the depth first search to find the distance from the target node to every single leaf node, right? So you can do distance to leaf, or I can just CFS here, right? Starting from the let's say the target node and the distance at 0. CFS equal to node. Okay, so the first base case, right, is if the node is null, it will just return and not do anything. If it is a leaf node, which is no 0, we want to return, right? We need to keep track of the distance, right? And the node and the leaf node value. So distance to leaf or push, we want the node value, node dot val, right? And then the distance, which is the distance. And yes, because we need to keep track of the distance too, because we need the distance, right? We're starting from 0 here. And then that is our base case. Our recursive case is we can look at the node dot left and then increase the distance by 1, right? Look at the left, look at the right, and we also look at the patterns, right? And remember, we need to keep track of the visited node. You can do visited.add, node.val, right? And we need to create that as well. New step. And we need our array for the distance, right? The 2D array. Okay. And our base case, right? If the node is null, we return, or if visited.hash but node.val, then we also want to return it. And we also want to return and add the node value and the distance when we see a leaf node. Right in here, we just keep track of the visited node. Okay, so that is step number 2. And step 3, after we finish setting the pattern pointer, finding the target node, and finding the distance from the target node to every single leaf node, the last step is to find the distance, right? So we can do closest leaf, right, from target. We can start from the target node. Okay. Let's don't call this node, let's call this data. Looking for mean node and mean distance, right? Equal to data 0. This is our 2D array, right? And we can start from in the front. We have our current node and the current disk here. Node of data by. If the current distance is smaller than the minimum distance, then we want to set the minimum distance to the current distance and also update our minimum node, right, to the current node. Right, that's pretty much it. And we can return our minimum node at the end. Okay, so let's give it a try. Cannot iterating through data 0. Oh yes, why am I passing in the target node here? I'm supposed to passing in the 2D array, right? The distance to the leaf. Yeah. And yes, this should be a less, right? Because I should be able to, because I want to be able to update the node. Okay. So what is the error here? We're starting from the target node 0, closest distance from the target, passing this to leaf, minimum node, minimum distance. Yeah, node and then distance. If current disk is smaller than the current node, this current disk is smaller than the minimum disk, we update the minimum disk and update the minimum node, and we will return at the end. So this function is correct. Let's look at this function, DFS, target node 0. We want to return right? Yeah, that's right. Interesting. Okay, so I found out that like I should be calling the parents here because we are going left, right, and the parents, right? It's a typo here. So it should work now. Okay, and thank you for watching.